In this video, we'll be talking about the language of mathematics and the fact that the mathematical language is brief, concise, compact, gives it the power that it has and makes it the language of science and engineering. What you're looking at here is a puzzle. So we're just going to consider something fun, which is how to do some representation using graph theory. And that will be one example of the power of the mathematical language. So this little puzzle is known as instant insanity. You'll notice that I have these banded together because if I take the rubber band off and the cubes fall apart, then I won't have a solution to this puzzle anymore. And there are actually 41,472 different ways to line up these four cubes. So if I wanted to try to solve this puzzle again, if it just fell apart and I needed to try to do it by trial and error, I would be in a lot of trouble. So what constitutes a solution here is that you need to have one of each color showing on each face. So you see we have yellow, red, green, blue. If I turn it, we have blue, yellow, red, green. No repeats of color on that side. And then yellow, blue, green, red. And then green, red, blue, yellow. So we've gone all the way around. We've seen that all four sides show each different color. But again, if I take this rubber band off and I just let these fall apart and kind of scramble them up, and I was asked to solve this again using trial and error, that would be a pretty daunting task, given how many options there are for how I can put these things together. If I wanted to send you directions either for how to solve this puzzle or for how to create a set of cubes like these of your own, that would be a somewhat challenging thing to do if I wanted to describe these cubes in words, for instance. At most, I can only see three sides at the same time, and the other sides are hidden because the cubes are three-dimensional. So let's think about how we might be able to describe these with a drawing instead. So let's just grab one of these cubes. And one thing I could think of, because the issue is that it's three-dimensional, how about if I open it up and have a two-dimensional view so that I could put that on a flat piece of paper? So if I were able to unfold this cube as if this were a present, and I'm very carefully cutting off the wrapping paper. So let me use this to give you a good description. So I notice that this side is blue. Let's just use B for blue. And this side of the wrapped present is red. So we'll put an R. The side down here that it's sitting on is green. And what's going to go up here? Well, that's this side right here, which is also green. And then if I come down this way, well, this is yellow. And this top face that we've been seeing all along, I could roll that down, and I see that that yellow face right there is going to end up right here. So I could send this along to you. That would be a description of what this cube is like. And so you could get a cube, a blank cube, and some paint. And you could paint it to be exactly like this one. You've got the blue and the red, you've got the green down here, etc. And you'd be able to get all those pieces. But there's actually a shorter, more compact way of writing this, and we can do that using graph theory. So I'm going to first begin my graph. The vertices are going to denote the colors, so we have red, green, blue, yellow. It doesn't matter what order I put those in. And what we're going to do, something that doesn't change, is what faces are opposite each other. So blue and red are opposite. No matter how I twist this and spin it, no matter what I do with it, blue and red are opposite each other. So what I'm going to do is put in an edge connecting red to blue. So I've taken care of that axis, or that pair of opposite sides. So then look, don't I also have green to yellow, which are opposites? And no matter how I spin this around or what I do, I'm going to get green to yellow. And then what haven't I done yet? I've got the green yellow that my fingers are on. I've got the blue and red. Oh, and then I have another green yellow. So you know what? I'm just going to connect those again. And this is actually a set of directions. The edges represent basically the axes, and then you see which two colors are on opposite sides of each other. So if you understand this language, and I realize it takes a little getting used to, but it doesn't take too long, you could grab a blank cube and some paint, and you could say, well, I need a side that's blue, and opposite that I'm going to have red. I need a side that's green, and opposite that I'm going to have a side that's yellow. But you know what? I need to do that again with yellow to green. And we're going to run through that process one more time just so you get an extra example. So if I want to send you directions for how to make this cube, which is a different cube than the one I was just working on, well, one way to do it would be to use this drawing, which is known as a net. So let's see. This is green, and this side over here, oh, that's green as well. Where's that red one going to go? Do you remember from the previous one? Isn't that going to come on down here? Because if I roll this out, that's going to be that red side. Here we have green. The thing that's facing the bottom is blue. And then what gets filled in here, well, that's going to be yellow. So you could take this diagram, you've seen how I created it, and you would just basically have to work the process backwards. But what would this look like as a graph? So again, we'll just say red, green, blue, yellow. And let's see. So I have red, and what is opposite that? That is something that doesn't change. So we have red to blue. Oh, I had that last time too. All right, cool. And then, let's see, we have green here and yellow. We have green to yellow. So I've done the green to yellow and the red to blue, so what is left? Well, I haven't done the sides that are both green. Those are opposites that are the same color. How are we going to represent that? Well, we say that green connects to green. One face is green, and the face on the opposite side is also green. So, if I gave you a graph, could you reverse this process and turn this graph into a cube? Well, let me make one up. Here's our graph. We have red, green, blue, yellow, and let's say I have red to yellow, red to blue, and red to green. So as long as I have 3 edges, I'm good, because a cube has 6 sides, which means it has 3 pairs of opposite faces. So I'm going to actually paint a cube, and we're going to start with red to yellow right here. I'm just gonna darken that so I remember where I am. I'm gonna do the red to yellow. And I just have a blank cube from a hobby store. So this side is going to be painted red. And then I'm going to paint the opposite side yellow. I hope that's staying in focus because I keep moving it up and down. I guess I'll see when I have the finished video. Yeah, my brushes are a little bit stiff and old, but you get the idea. So we've got red opposite yellow, which is this edge right here. I'm going to set this down and let it dry for a little while, and then I'll come back and do the other 2 pairs of opposite sides. Well, this isn't quite dry yet. Again, we have the yellow and the red. We've taken care of this edge. I'm going to go next for red to green. I may regret not waiting for it to dry longer, but I'm feeling impatient. So I need red and green. And by the way, it doesn't matter if I do red to green here or if I do red to green where my fingers are right now. So the top and the bottom, or the front and the back, so to speak, because it's just a matter of a rotation. So this is actually the same thing as this. So we're going to go red to green. Okay, there's the red. And on the other side, we want to go with green. And in a few moments, I'll come back and do our last pair of sides, which is red to blue. And now we're going to go with the red to the blue, which is the only edge that is left. So I need a little bit of blue paint. And let's go ahead and do that. So we're going to have yet another red side. We have quite a lot of red on this cube. To blue. So there you have it, from just 4 dots or vertices and 3 lines, which we call edges. I've now completed this cube that we have the directions for. Now I'm making this video in the midst of the COVID pandemic, so I'm obviously not going to have students making cubes and turning those in because there would be no way to do so. So what I will be asking you to do is to be able to go back and forth between the representations that we had earlier, to be able to see a graph like this and then create a drawing like this, or vice versa. So something to notice here, we see that red and blue are opposite each other. Well, where are those? Here's blue and red, and those are 2 spaces apart. If you were to fold this up, these would be opposite each other. Similarly, we remember that when we have this loop connecting green to green, that those are opposites, and you'll notice that those are basically a space apart, right? There's something else in between them. And then yellow and green are also paired. If you were to fold this up, those would be on opposite sides of the cube, and we see yellow to green right here. So let's try one of those. If I give you this graph, let's see, and I'm going to want 3. Let's have it look like that. So that's 3 pairs of opposite sides for the 6 sides of a cube. Can you take that and put that in the net, the unfolded cube? Try it. While I'm drawing mine, see if you can do yours. There it is again, if you need to copy it over. Okay, so the opposites are going to be every other. So I see here a red to green. So let's do that one. And I'm just making it kind of bold so I can keep track of what I did already. And then let's do green to yellow. And we have 2 different options for this green to yellow. We can put it here or we can put it here. And it actually doesn't matter. And that has to do with the fact that the cube can be rotated. So let's just keep going down. Let's say we go green to yellow. And then we have one left, which is yellow to blue. And that's going to fill in this part over here. But then I want you to be able to go the other way as well. So let's say that I give you a net, an unfolded cube. These are very, very sloppy, but hopefully you get the idea. So let's say we have yellow and red and green and blue and red. What would that look like on a graph? Well, we have yellow to green. So I've done these. I'll just check them off maybe. Those are opposites if we fold this up to make a cube. We've got red to blue, which are opposites. Done those. And then we also have, oh, we have another red to blue. So we're going to indicate that this way. We just connect the red and the blue twice. So you've now been introduced to the game Instant Insanity. More importantly, you've been introduced into how we can use mathematics as a concise language for representation. I'm just going to quickly show you. Here I have a copy of the game that's manufactured rather than homemade. So you can purchase these or you can make your own if you're interested. Under normal circumstances, I would get students into groups in the classroom, and I would actually talk students through how to solve this. So I'm going to show this to you quickly. Those of you that are interested in looking into it further, you can find these directions online. But basically, when we're able to be in the classroom, I talk my students through why it is that there are more than 40,000 different ways to line up 4 cubes like this. Then we represent each of the 4 cubes individually. We take all 4 of these graphs and we smash them together. So that's here. And then we look for certain aspects that we want to pull into 2 separate graphs, one representing front back, the other representing top bottom. And you might want to think about why there are 4 edges here instead of 3. And you might want to think about why each color has 2 edges coming from it. But then what we do is we take these and we write this out so it's a little easier to use. This is actually a set of directions for how to solve the puzzle, but I usually take that and write that into words. So that was one semester with my students, and then here's a setup from another semester where I walked my students through the same thing. So the takeaway from this video, what I'm going to want you to do is to be able to go back and forth with representation, be able to go from the net to the graph and the graph to the net. But the other takeaway is, look, you can represent a graph. You can represent a colored cube using just 4 dots and 3 lines. So math is a very concise, brief language, and that is one of the things that makes it powerful. This may be just kind of simple, right? It's a silly little puzzle. It's nothing earth-shaking, but again, hopefully it gives you the idea for how the language of mathematics is very brief, which makes it powerful, and there are lots of different things we can do with it. Things that are this simple and playful, and things that are bigger and more important as well.